Fubini's theorem or double counting method is very important for probability distributions, rather conditional probability distribution calculations. So when you change the integrals or the summation sign. So today I will use a very simple example to demonstrate the power of it. So we all know the summation of I square 1 to n is this expression, right? So the goal is to use, so this is in quadratic form. The goal is to use this linear form to derive this. Only this, we can only use this linear form to derive that. That's the only constraint. So how will we do this? To do that, we will use something called Fubini's theorem or the double counting method. So what we will do here is we will rub this off. We will write this off somewhere else to remember the expression. So let's rewrite this. So observe, so the first question is that how can we write I square in terms of summation of I or in this format? And you can itself say that the summation of I over 1 to I from 1 to n is a quadratic term. So can we replace this by some summation? So if you observe this, you will see that square is nothing but the summation of the odd terms. So we are using this result here, let me write it down here, that summation of I from 1 to n or rather x from 1 to n is 2 of the odd terms is, or rather 1 to I is I square. So that's an odd term summation. Okay? So we rewrite this, the I square, as an odd term summation. So we'll have this two summations to x minus 1, x from 1 to I. This gives the I square and I from 1 to n. So this is what we have to find. Okay? Now understand that the Fubini's theorem is double counting. So we have to reverse this aspect, this I and x, to find the actual summation. That's the whole idea of Fubini's theorem, the double counting method. Again, I am repeating, it's very, very, very important for conditional probability calculations. So stay focused. So what we will do here is we will graph it. Like on what is the structure of the support of I and x together. So we'll graph it. So let's draw the graph of I here and x here. And you will see, so let me see, I have drawn some notes so that I don't make any mistakes while speaking. So if you'll see, this line is I is equal to x, and you can see x is always less than equal to I because I is going from 1 to I. X is going from 1 to I. So x is always less than equal to I, and I is going from 1 to n. So it's kind of in this region. It's kind of in this region, right? X is taking these discrete values. X is going from 1 to I till this. So this summation can be expressed as x is taking from 1 to I to that corresponding I. It's taking the each of these values. The support looks like this. It takes from each of these values and I is moving from 1, 2, 3, n. So the support, the progression of this summation is like this. So it's counting the number of points here actually. So if you look at the points, if you count the points, essentially it's counting the number of points. Okay? So can we represent this number of points, this support, this progression of I and x together in a different way? And yes, we can. So what we'll do, we will, instead of doing this vertically, we will do this horizontally. So if you go from I from 1 to n and do the same graph, so here it's x, here it's I. Let me see. So we will go first, so we will reverse summation as summation of, first we will go from I over, we will sum over I, and then we will sum over x. Okay? So we will now do this horizontally. So the same points can be covered vertically, the support, and the same points can be covered horizontally. This is the whole idea of double counting. And we will now represent the set of points, the support, in a horizontal fashion, because here it was x and then I. Now we will do I and then x. Okay, that progression. This is a very important concept. So we will do this like this. We will count the support like this now. So now observe that I is now, the minimum value of I is now x, because this is the I is equal to x line. So it's going from x to n. So I is going from x to n, and now x is taking 1 to n. It can take all the values now. Okay, before it was taking only 1 to I, now it can take all the values because we have reversed the entire support, the region. So x is now going to 1 to n. And now we get the same expression. So this is the beauty. So observe that now this expression, the I, there is no I here, so we can take this outside. X from 1 to n, get 2x minus 1 times this is n minus x plus 1. Let me see if I've done it correctly. I think so. Yes. So we'll count this. Now you can see it's over a single dimension, but we will see there is x square is coming up somewhere here. So we will see the fun part. So let's call this as f of n. This one. Okay, let's call this f of n. And we will see how this emerges. So let's erase this part, because we already understood it. It's not algebraic calculation. So we will write this here. So we'll expand this. Summation x from 1 to n. We'll expand this. So we'll get 2. We will have 2x minus 1 times n plus 1. Right? 2x minus 1 times n plus 1 minus, the minus x is there. So minus 2x square. So we will have minus summation of x from 1 to n 2x square plus the plus x, minus 1 minus x is plus x. So plus summation x from 1 to n x. So observe this very carefully now, that the n plus 1 is constant and its summation over the odd, which is I square. Here it's going to n, so it's n square. So it's n square here. So this one is n square minus 2 of x square. The good thing is that this is minus of f of n. So minus of twice of, this is the f of n, plus this is n into the same thing, the linear, the one-dimensional aspect, n by 2. Now it's very beautiful. So we have got f of n is equal to minus of 2f of n plus this quantity. And if you calculate this, n square times n plus 1 plus n into n plus 1 by 2, and if you calculate this, you will get, let's see what we will get. You will get beautifully, you can check it out, n into n plus 1, because you can take that common, times 2n plus 1 by 2. It's beautiful, right? We get this n into n plus 1 into 2n plus 1 by 2, and see, observe this, what we have here. So we can now replace this as 3f of n is equal to this quantity. And we want to find f of n. So this goes to, oops, I broke a chalk. This is the worst part. Never break a chalk. It looks so beautiful as a whole. I broke 2 chalks. Anyways. So f of n is, we go take that 3 on the other hand side and we get f of n is equal to this quantity. So the most important part here is not the algebra, but this part of how we change the two integrals, rather the summations here in this case. Sorry, this two part. How we change the two summations together to get the final expression. This is the most important part. This is the Fubini's principle. This is the double counting method, which is very, very important for probability. for conditional probability calculations, because often in conditional probability calculations you will come up with these summations, these convoluted summations when the random variables are separated or rather are related in this fashion of this geometric fashion, like I have shown in the example in the diagram before, in that convoluted support space, how they are related to each other. So this idea of Fubini's theorem can help you find out those summations very carefully, very elegantly. Because when you do this change, now it was entirely dependent on two different methods of counting. So when you do this, what happens is that you can change that convoluted pair of random variables in probability into something easier, into a probability distribution counting which is much easier to handle, which is something known to you. That's why in probability problem solving this is extremely important, guys. Okay, this is Fubini's theorem for you. I will see you in the next video. Bye bye. Another chalk.